Good afternoon. Alright, today I'm going to do a video on how to determine whether a molecule is polar or nonpolar. Alright, so the first molecule that I will draw out is Boron Trifluoride. Alright, so Boron Trifluoride is, here's the structure, right? So if we do the Lewis structure, we know that boron is in group 3, so there are 3 electrons for boron, and for fluorine there are 7 valence electrons. There are 3 fluorine, so we have a total of 21 electrons for fluorine, and if we sum that up, 3 plus 21, we get a total of 24 electrons. Alright, so we have 24 electrons. Alright, so I'm going to put boron in the center because it is the least electronegative atom. Fluorine will go around boron, so we have those 3, and then each bond represents 2 electrons. So 2, 4, 6 electrons. So I'll subtract 6 from 24. That leaves me with 18 electrons. And I'm going to assign fluorine. So each line represents 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Alright, so we have our structure for boron trifluoride. Alright, and so one way to determine whether this molecule is polar or not is if we basically depend on electronegativity, right? So we know that going from left to right in the periodic table and bottom to top, we know that boron is the least electronegative and fluorine is the most electronegative. So I'm going to draw this arrow that has a little cross at the end showing the direction in which the dipole will go, because a dipole is just simply a vector that shows magnitude and direction. Right, so let's see if I can change the color here. Right, so we have, alright, so the positive part of this arrow is because boron is the least electronegative, or the more positive atom, and what's happening is the electron density from boron is being attracted to the fluorine molecule. So our vector goes in this direction for each boron fluoride bond. Right. Alright, so we have 3 of these polarized. They are polarized. However, because these vectors are, because each bond is the same, the vectors cancel each other out. So that makes this molecule a nonpolar molecule. Right, so I will just put nonpolar NP. Right. Alright, so the next molecule that I'll show you is ammonia. And so ammonia, writing this out in H3, ammonia, if we draw the Lewis structure, we know that nitrogen has a valence of 5 electrons, hydrogen has a valence of 1, and there are 3 of them, so times 3, and we get a total of 3 hydrogen atoms, or hydrogen electrons. If we take the sum of those two, we get 5 plus 3, which is 8 electrons. So we have 8 electrons total. So when we draw the Lewis structure for ammonia, we want to put our nitrogen in the center. Although nitrogen is more electronegative than hydrogen, hydrogen can only be bound to one other atom. So we call these type of atoms terminal atoms. Alright, so again, each bond represents 2 electrons. So far we have 2, 4, 6 electrons. Right, so now we have 2 more electrons to work with, and those electrons are going to go on the nitrogen. Alright, so, and I'm going to draw my arrows this way, right, which means that the least electronegative atom, hydrogen, has electron density that is being pulled by the more electronegative atom, nitrogen. So the direction is going in one direction towards the nitrogen. Right, not only that, but we have these lone pair of electrons on the nitrogen, and anytime you have a lone pair of electrons on the central atom of a structure, that indicates that your molecule will definitely be a polar molecule. So anytime you have lone pair of electrons on the central atom, which is nitrogen in this case, your molecule overall will be polar. Alright, so let's take a look at sulfur dioxide. Alright, so sulfur has a valence of 6. Oxygen has a valence of 6 as well. There are 2 of them, so we get a total of 18 valence electrons. Alright, and so with this molecule, I'm going to put sulfur in the middle. Alright, and then oxygen, being the more electronegative atom, will be on the side of sulfur. So we have 2 oxygens here, and so far we've used 2 4 electrons. And so take note that oxygen is divalent, so we can actually make this a double bond, so 2 4 6 8, and then we'll put 10 12 14 16, and we're left with 2 more electrons, so those electrons will go on sulfur, 18. Alright, so the structure that we want to use, now take note that sulfur dioxide can also be written this way. Right, so we have single bonds versus double bonds. And when we remove a bond from the sulfur and the oxygen, we create two electrons. So those double bonds that were between the sulfur and oxygen become lone electrons on the oxygen. So we have 2 4 6 8 10 12 14 16, and then our sulfur will still contain 1 lone pair of electrons. The correct or the best structure would be to use this first structure. And the reason is because we want the most covalent bonds. So the structure that has the most covalent bonds is the best structure to work with. So we're going to work with the first structure. And I'm going to redraw it here. 1 2 3 4. 1 2 3 4. And then I'm going to put my lone electrons here. Alright, so once again, anytime you have a lone pair of electrons on the central atom, your molecule is automatically a polar molecule. Not only that, but because of these electrons on the central atom, it causes the geometry of sulfur to really look more like this. More of a bench-shaped molecule. So it's not linear, it's more of a bench shape. Right? And that's because of the electrons on the central atom sulfur. It causes the molecule to be slightly distorted, giving it a bent geometry. So we get a polar molecule. Alright, so let's take a look at carbon dioxide. Alright, so carbon we know is in group 4, oxygen is in group 6, and there are 2 of them. So we have a total of 12 plus 4, 16 electrons. Alright, so I'm going to draw out the Lewis structure. And once again, we want the structure that has the most covalent bonds. That's the most stable structure. So that would be the best structure to work with. Alright, so 2 4. And then because oxygen is divalent, it should be bound to it should have 2 bonds, whether that be oxygen bound to 2 atoms or having one double bond. So we're going to say 2 4 6 8, and we have 8 more electrons to work with. So that's 10 12 2 4 6 8 10 12 14 16. Alright, so in this case, carbon dioxide does not have a lone pair of electrons, and the shape for carbon dioxide is actually linear because it doesn't have those lone pair of electrons on the carbon, so there's no distortion, there's no repulsion that takes place, so we get a linear shape. Not only that, but the electronegativity for carbon is about 2.5, whereas for oxygen is about 3.5. So the dipole would actually go in this direction, right? Starting with the least electronegative atom to the most electronegative atom. And because those 2 bonds are the same, they'll cancel each other out, and so you get a nonpolar molecule. And so that is my talk on how to determine whether a structure is polar or nonpolar, and I hope this helped. See you guys later.